All right, guys. So today we're going to be comparing graphs of a function, the graph of its derivative, and the graph of its second derivative. So let me kind of give you guys a brief little overview. So if I were to tell you guys that this was my function, y equals x squared, right? Then what would its derivative be? Its derivative would be that. And the second derivative would be that. Now let's look at their graphs. For the function y, this is my x-axis, and the outcome is like my y value. It would look something like this. For this one, we still have an x-axis, but my output represents my derivative now. So the height now represents the slope. Okay, it's no longer just y. And that graph would be y equals 2x. So that has a y-intercept of 0 and has a slope of 2. So that, if you were to graph that line, it would look like that. And then finally, for this next one here, we still have an x-axis, even though there's no x's in the problem. But the output now is the second derivative. And if you were to graph this, y equals 2, well, that's just a flat line, right? Now, we want to remember that y prime represents the slope of y. And we want to remember that y double prime represents the concavity of y, the original function. So the derivative tells us the slope of the original function, whereas the second derivative tells us the concavity of the original function. Now, since the second derivative is the derivative of the first derivative, you could also say that the second derivative is the slope of the derivative. Okay, so this is the original function, and then we have its derivatives and how they relate to each other. Now, today our job is going to be not by looking at equations, but looking at the graphs. If I tell you that this is a graph of y prime that looks like this, you should be able to derive from that what the graph of y prime might look like, or what the graph of the second, or what the graph of the original would look like. In the same way, I might tell you what this is, the derivative. And from there, you might be able to tell me something about what the graph of the second derivative looks like, or the first derivative. Okay? And then also, we could go from here to the other two. So the point is that today we're going to be looking at a function, its first derivative and its second derivative, and starting to see what elements of that look like on a graph. That's kind of our task. And we're going to be working on that for the next 3 days. It's actually a very important topic, and it covers a broad scope of questions that you'll be asked on the AP exam. So that's why I want to spend so much time on it. I really want to make sure that you guys have got this comparison of the graphs of f prime, and f double prime. So what are we doing specifically for our first day? Well, today we're going to start by using the graph of an original function f to determine where its first derivative and second derivatives are 0, positive, and negative. So we're not going to look at graphs of the derivatives yet, but we're going to use the graph of f to discover some facts about the derivatives. And then also I'm going to give you some facts about a function, its derivative, and its second derivative. And from that, you should be able to turn that into a graph of the original function. So that's what we're doing today. So today our main stomping ground is with the original function and deriving some facts about derivatives. Our next few lessons will actually flip the story a little bit and start with the graphs of derivatives and work our way around that. All right, so let's begin. So I've already kind of talked about this with you guys already, but if you want to add it to your notes now would be a good time. F represents a y value. okay, of your original function. F prime represents the slope of your original function. And F double prime represents the concavity of your original function. It could also be said to represent the slope of your derivative. Okay? So that's what those derivatives represent when you're talking about graphs. All right, so here's our first objective today. This is a graph of f. We might want to add that to our instructions. That's kind of important. The graph of f is given below. That's important because in the days that follow, the graphs we're going to be looking at are not going to be graphs of f. Instead, they're going to be graphs of the derivatives. So it is important that you know what kind of a graph you're looking at. Okay? So in this case, the x-axis represents the value of x, and the vertical axis represents the value of y, the original function, the output of the original function. So these here then would be y values. So let's start there. When we're just talking about f, those are just the y values. So where at on this graph is the y value equal to 0? Well, that would be anywhere it touches the x-axis. Okay, and so that would be right here and right here. And so if we were estimating, I would say that the one on the left looks like it's probably -2. And also probably at about 6.1 maybe, just estimating. Okay, so that's where f of x equals 0. Or in other words, where y equals 0. Okay, so let's go ahead and move on to the next part here. Where is f of x greater than 0? Well, once again, we're talking about the y values. So where are the y values greater than 0? Well, that would be anywhere that is where f is above the x-axis. Okay, so any point from here all the way to here has a y value that's greater than 0. Like, for instance, this point. At that point right there, the y value is 4, right? 4 is greater than 0. Or you could choose this point. At that point, the y value is 2. That's greater than 0. But you wouldn't want to pick a point down here because down there you've got y values that are less than 0. So basically, f of x is greater than 0 anytime it's above the x-axis. And therefore, in this case, it doesn't happen at a single point. Instead, it happens in a whole range. So anywhere from x equals -2 to x equals 6.1, it's above the x-axis. So f of x is greater than 0 when x is between -2 and 6.1. So for all values of x between -2 and 6.1. Now you could also write your answer like this, which is probably how I'll usually do it, honestly. The unfortunate thing about this is it looks like a point, but it's not. This is an interval. I'm not saying this is an x value and this is a y value. this is an interval starting at x equals -2 to x equals 6.1, and these parentheses mean that the endpoints are not included. Now, why aren't the endpoints included? Well, I'm looking for where f of x is greater than 0. The endpoints are where it equals 0, which we already talked about in the first one. Now, if you wanted to include the endpoints for something, then you could put brackets, but in this case, we're not going to do that. All right, so let's go ahead and take a look at the next one. You guys could probably imagine what that one is. Where is f of x less than 0 now? Clean this up a little bit. Where is f of x less than 0? Well, if f of x is greater than 0 above the x-axis, then f of x is less than 0 anywhere f is below the x-axis. Okay, so that would be here, and we can pretend it keeps going. I don't know if the graph keeps going or if it just got cut off, but we'll pretend it just keeps going. Okay, so in that case, how would we write our answers? Well, anything to the left of -2. So from -infinity up to, but not including, -2 is a place where f of x is less than 0. And anything from 6.1 on the right side off into positive infinity. Okay, so I'm going to assume that these things just keep going. That's why I put infinity. But if there was a dot here at these endpoints, then we would stop where it tells us to stop. Okay, but I'm going to assume there's arrows. So go ahead and throw some arrows on your graph if yours doesn't have them either. All right, so that's how we can identify those parts of the graph of f. Okay, we're basically looking at the y values. When it's equal to 0, it's on the x-axis. When it's greater than 0, it's above. And when it's less than 0, it's below. All right, but now, given the fact that this is a graph of f, remember that's important. This is a graph of f of x. Where are these things happening? Now, this is talking about the slope. Okay? I think it might be a little bit easier to start by talking about where it's increasing and where f prime is greater than 0 and where f prime is less than 0. So let's start where f prime is greater than 0. Let's do this one. F prime is greater than 0 when f is increasing. Why is that? Well, if this is the slope, right, and it's greater than 0, a slope that's greater than 0 means that your graph is increasing. So I would be looking for a place on this graph of f where it's increasing, right? So that would mean we're looking for on our graph as we move to the right where it's moving in an upward direction. So for instance, that would be from -infinity all the way up until here, it looks like it's increasing. And then from here all the way up to this point, it looks like the graph is increasing. So those are places where the graph is moving in an upward direction as we move to the right. Okay? And so the answer for that one is going to be from -infinity, it's increasing, all the way until we get here, which is an x value of 0. So from -infinity to 0, f prime is greater than 0. Because from -infinity to 0, f is increasing, and when f is increasing, its slope is positive, and that's what this is saying. So from negative to infinity, and also from 2 up to 4. Those are x values, mind you. So from x equals 2 to x equals 4. And once again, we're going to be using parentheses. You use parentheses for infinity because you can never get there. And for the 0, because it's not actually a positive slope anymore at that point. And I'll explain why in a little bit. But since the tops there are not positive, then we don't include it. In fact, some of you guys might already know what that slope is because we've talked about it in other contexts. All right, let's go ahead and move on to the next one. Let's talk about where f prime is less than 0. All right, f prime is less than 0 when f is decreasing. So where is f decreasing? Well, decreasing means that we're going in a downward direction as we move to the right. So starting from here and going like that, we're moving in a downward direction that whole time. So we put a little arrow there to indicate the direction. Same thing here, moving in a downward direction over there. Okay. All right, so let's go ahead and write out those intervals. So it looks like f is decreasing from 0 up to 2, and then from 4 on into infinity. So those are the intervals where f is decreasing, and since f is decreasing, that means that its slope is negative. And if its slope is negative, that means its derivative is negative because the derivative is the slope. Okay? So that's how we can classify or find those things. Now, the next question, which I haven't done yet, is then where is it equal to 0? Well, the way that I've been telling you guys to find up to this point is where f has a horizontal tangent. A flat line. Now another way you can find it is where f changes from increasing to decreasing. Okay, so like right here, for instance, we change from pink to green. In other words, we're changing from increasing to decreasing, or vice versa. In other words, here is also another place because we're changing from decreasing to increasing. If you're changing from positive to negative, the only thing that must be in between those would be 0. So right here is where you would have a horizontal tangent line, and right here is where you would have a horizontal tangent line, and the last one is up here, the last place where we're switching from pink to green, which would also be a horizontal tangent line. Okay, so there you have it. So now those are not intervals, those are points. And so there are very definitive places where f prime equals 0. And those are at x equals 0, at x equals 2, and also at x equals 4. Okay? So points we represent with an equation like that. Intervals we represent with the parentheses. So that's for f prime. Let's go ahead and talk about f double prime. Remembering once again that this is a graph of f. Well, if this is a graph of f, then f double prime would represent the concavity of that function. Okay, so once again, I think it'll be easier to talk about where the second derivative is greater than 0 and less than 0 first. So let's start with greater than 0. When the second derivative is greater than 0, that means that f is concave up here. Okay, so where is f concave up on this graph? Now some of you guys, I think you're probably going to get really close, but you're going to make a mistake. Some of you guys might think, oh, it's concave up from here to here. That's not true, but you're close. I would say that it's more likely to be concave up from here to here. Okay? And the reason for that is because I would say that at this point, it's still bending in a downward direction. So here we have a downward bend, same thing here. And so a good way to find where it switches concavity is, if you're going from one peak to another peak, a good guess, it's not like true, okay? This is not 100% true, but it's a good guess when you're estimating on a graph, okay? Where it changes from concave up to concave down, I would just say somewhere right in the middle of those two peaks, peak 1, peak 2. Just find the middle point. Same thing here, from this peak to this peak, the middle point, I'd put right about there, right? And so that's where I would say the concavity is changing. So all that being said, let me erase all this. We were talking about where is f concave up, and we come to the conclusion it goes from this middle, the middle of the peaks on the left to the middle of the peaks on the right, and that's a pretty good guess. And now we can give the x values. This x value here would probably be about x equals 1. And this x value here would probably be about x equals 3.5. And I'm just estimating, you guys. So if you put 3, that's okay. It doesn't matter. The point is, are you getting pretty close to it, right? We don't have exact answers for this. So from 1 to 3.5, I would say that the graph is concave up. 1 to 3.5. And just remember, another way to write these intervals that, in my opinion, is a little bit less confusing, but since we use this so much in calculus, I just keep using it. But I like writing my intervals like this a lot of the time also. I just feel like that's a lot more clear, so you don't accidentally think that this is a point, because it's not. It's not an x value and a y value. It's two x values. All right, so there's that. So now let's move on to the next one. The next one is asking, where is f double prime less than 0? Well, that would mean that it's f is concave down. And we've already kind of seen that a little bit earlier when I was making my explanations, but I would say that would be from here to here, then from the halfway point of the peaks and onward. So I'd say those places are where f is concave down, okay? And so that would be from negative infinity on the left to 1 on the right, in tandem with 3.5 on the left here, off into infinity on this side. Okay, and so that's where f double prime would be less than 0. And so now for our last question. Now that we know where it's concave up and where it's concave down, now it's a little bit easier to answer the question, where does f double prime equal 0? Well, once again, 0 is right in between positive and negative, right? Positive numbers and negative numbers. Well, then where we go from a negative second derivative and into a positive second derivative, that point where it switches concavity would have to be the place where the second derivative is equal to 0. And so I would say that x equals 1 is a place where we have an f double prime of x equals 0, and also at x equals 3.5. Now, on the graph of f, those are called points of inflection. So when f double prime equals 0, you're looking for the points of inflection, or the place or where f changes concavity. Okay, so that's what we're looking for. So once again, we're comparing the graph of f to derivatives and second derivatives in today's lesson, and your job is to be able to look at a graph of a function and find where its derivatives and second derivatives are positive, negative, and 0, and also where that function itself is positive, negative, and 0. So these are y values, these are slopes, and these are concavities. Okay, so let's go ahead and throw a student practice at you guys. Here's one for you. Pause the video, and when you unpause it, you will see the solution. All right, so go ahead and check your answers here really quick. Pause the video and check your answers. When you unpause it, I'll explain the answers in case there was something that you didn't get correct. So for the first set here, these are the y values. So where does y equal 0? Well, that was anywhere it touches the x-axis, which is here at x equals negative 2. Where is f of x greater than 0? Well, that's anywhere our graph is above the x-axis. So that would be from negative 2 on up into infinity. It's always above the x-axis after that. So that would be from negative 2 on into infinity. And where is f of x less than 0? Well, that's where it's below the x-axis. So that would be from here and down. And so that's from negative infinity up to, but not including negative 2. All right. These are the slopes. The first derivative is positive anytime f is increasing. So that would be from negative infinity up to here, and from here on into infinity. So that would be from negative infinity up to 0, and from 2 on into infinity. Where's the first derivative less than 0? Well, that would be where f is decreasing. So that would be from here to here. It's moving in a downward direction. And so that would be from 0 to 2. Oops, didn't want to do that. All right, next. Where is the second derivative equal to 0? It's where it changes concavity. It's the point of inflection of this graph. So I would say that it's concave down from here up to that midpoint between the peaks, and then from that midpoint of the peaks on into infinity. And so I would say that the point of inflection is probably right here. And so the point of inflection is going to be at about x equals 1. The second derivative is greater than 0 on the green section, so that's from 1 to infinity, and it's less than 0 anytime the graph of f is concave down, which is the pink section there, from negative infinity up to 1. And so there is the solutions to your student practice. So that's one thing, is you guys should be able to look at a graph of f and find all this sort of information. All right, now we're going to do another thing. I'm going to give you some information about a graph. I'm going to tell you about some y values. I'm going to tell you about slopes and concavity. And your job is going to be to sketch a graph of it. So we'll start off with an example and we'll move into a student practice after that. Okay, so let's go ahead and do this. We want to use this information that they're telling us about the y values. They're telling us some stuff about the slopes and the concavity. And our job is going to be to create a graph. And basically, my suggestion would be just to start with the y values, then move on to the slopes, and then move on to the concavity. And honestly, by the time you get to concavity, most of your work will probably already be done, and you're just checking to make sure that this works. So let's jump in and see how that works out. Okay. Make a graph here. So first we have this. These are points where the y value equals 0. In other words, those are where it touches the x-axis. So let's go ahead and put some intercepts on there. So we have one intercept at 3, at an x value of 3, y equals 0. At an x value of 5, we have a y value of 0. And at a y value of 8, x value of 8, we have a y value of 0. Okay. Now next, we're going to be looking where are y values above the x-axis? Well, it tells us that it's above the x-axis from negative infinity up to 3. So from here and over, it's got to be above the x-axis. Now, you're going to want to be using a pencil for this, just so you know, because we're probably going to have to change some things along the way. Okay, but for now, what we do know is that it's above the x-axis. So from here and over, it's up above the x-axis. And then also from 5 to 8. So from here to here, it's above the x-axis. Between 3 and 5, it should be below the x-axis. So now I have to make these loops because it needs to connect those dots. Right? We know that those dots have to be on our graph, so it can't go down forever, right? It's got to start here, come back up, and hit that dot. So that's why it looks like a little loop. All right. And also it looks like we have it being below the x-axis from 8 on into infinity, so that would be like this. So that's what my graph looks like so far, just based on the y values that they told me. Okay. So now let's go ahead and move into talking about the slopes a little bit. Okay. So the slopes, I see here that I should have a 0 slope or a horizontal tangent line at 1, at 4, and at 6. So I should have a horizontal tangent line right here. So it should be flat here. So now there's two ways that could happen. Okay, and this is where you kind of just got to get creative, but there are two ways that could happen. So now I've got to make a change to the left side there. It has to stay above the x-axis because we said that side has to be above the x-axis. One way that could happen is if it goes like this and then it comes down. But remember, it can't go below the x-axis, so maybe there's a horizontal asymptote. I went below there by accident because I'm having a hard time using this little drawing tablet I'm using right now, but it's supposed to stay above the x-axis. Another way that can happen, let me take some of that away. Drew a little bit more than I wanted to. Try one more time. There we go, that's better. Now another way that could happen would be as if it came up like this. Let me use a different color. Is if it came up like this, got flat, and then it's continued to go up. So we'll see which one of those it is. Is it the one where it goes up? Or sorry, is it the one where it's, you know, pointing in an upward direction over here and then it gets flat and then here? Because we need a zero slope here. That's all that I know for sure. Or is it where it's one where it's going in this direction and it makes more like an upside down shape? All right, so we'll see. We have two possibilities there. All right. We also need a flat slope at 4. So here's 4, and that already looks like a flat slope to me. Okay, and at 6. So here's 5. Right now, I've got my flat slope probably like at 6.5. So, you know, I might change that a little bit. It's not a huge deal. But if I were to change it so that I have a flat slope at 6, maybe my graph would have be a little more skewed to the right like that. Okay, there we go. So now I've got our zero slopes in there, but the rest of it looks okay. The only one that's questionable is what's happening over here. So let's go ahead and take a look at the rest of it. This is indicating that my graph is concave. I'm not concave up, sloping up. So from negative infinity to 1, we need a positive slope. So let me ask you, which one of these has a positive slope? Does this have a positive slope? Or does the other one that I drew have a positive slope? Which one of these lines has a positive slope? Well, hopefully you guys know it's the one on the bottom. So now I know it's not the one on the top, it's the one on the bottom. And so now I'm going to go back and adjust this a little bit more. I'm going to get rid of, I don't know if it's going to let me just a second here. Yep. So now we've got that little situation going on. Let's check the rest of it. We also want to make sure that my slope is positive for between 4 and 6. So here's where x equals 4 right down here, and x equals 6 here. So yeah, we're good. That's all a positive slope from there to there. We want to make sure that the slope is negative from 1 to 4, so from here to here. And yes, that's all a negative slope. And from 6 to infinity. So you guys can see, after you've already done some of it, the rest of it just starts to naturally fall in place. Let's go ahead and keep checking the rest of it, though, because we're not quite home free yet. Let's make sure that the second derivative pieces are lining up the way they're supposed to. So I'm supposed to have a second derivative of 0 at 2. In other words, there's a point of inflection at 2, which would be right about here. There should also be a point of inflection at 5, which is right there. And there should also be a point of inflection at negative 1, which would probably be like right about here. And so next we're going to ask ourselves, okay, so we want it to be concave up from 2 to 5. So that would be from here to here. Does that seem like a reasonable place to call concave up? I would say it's reasonable. And also it's concave up from negative infinity to 1. So from here, negative 1, to here. Yep, that looks concave up to me also. And then we have concave down from negative 1 to 2. And then from 5 on into infinity. And that also looks reasonable. So that all checks out. So once again, you guys can see after I got past like this third line, fourth line down or fifth line down, the graph was pretty much done. I was just checking to make sure the rest of the pieces fell into place. And so this is what your graph would look like. It would look something like that. And that is a graph that has all these properties. So that's what our objective was here. Our objective is for me to tell you various facts about the y values, the slope, and the concavity, and have you create a graph that meets all that criteria. Okay? And so start with your y's and just work your way down and add and adjust as necessary. So let's go ahead and throw one of these at you guys real quick. All right, so here's one for you guys. Go ahead and see if you guys can sketch the graph of that function. When you're all done, you can unpause the video and it will show you the solution. All right, so this is the answer. We have x-intercepts, or where it touches the x-axis, is at -2 and 6. So I've got a dot here and here. Notice that from negative infinity up to -2, it's above the x-axis, and also from 6 to infinity. And in between -2 and 6, it's all below the x-axis. Next, we have f prime of 0 equals 0, f prime of 2 equals 0, and f prime of 4 equals 0, which means we should have some flat horizontal tangent lines at 0, 2, and 4. So I drew a red horizontal tangent line here at 0, a red horizontal tangent line here at 2, and a red horizontal tangent line here at 4. And that means that my graph would have to go down, hit that, come back up, hit that, come back down, hit that, and swing back up. We can also check our slopes here to make sure that the slopes all match now. So from 0 to 2, so from this point up to this point, it should be positive. And from 4 to infinity, from here to here, it should also be positive. The slope should be negative from negative infinity up to 0, and from 2 to 4, which it is. Then the little orange dots represent my points of inflection. I have a point of inflection at 1 and 3, and you guys can see that on this side, we should have a concave up, and we should also have a concave up here, starting from those points of inflection. So those green areas are represented by these intervals. And then this interval is concave down. That would be from here to here. And the orange dot is where it switches concavity, and that's where the points of inflection equal 0. So your graph should look something like that. Okay? And that pretty much does it for our lesson. So with that, we'll say, have a good day, good luck with your homework, and we'll see you guys in class.